important things for society, namely the photovoltaic energy. So how we use this energy coming from the sun by having understood the quantum mechanics, and how after many, many years, he did never arrive to learn it, but how a Nobel Prize given almost 100 years ago to this, well, you recognize him, I hope, to Einstein, was transformed in something extremely useful for society, as many of other applications coming from his discoveries related to relativity and to the basics of quantum mechanics. So you have seen yesterday, for example, that the relativity, it's mostly used in the GPS. That's one thing, but now I'm going to talk about the quantum mechanics and one of its basic uses in a society. So the solar energy, it's something which nowadays it's rather common. We see when we go around many, many houses which are using it, and the part of houses, it started to be used in many other environments, like in airports or in parking places. And I'm going to tell you about and show you some of these discoveries. I'll show here a picture of how these kind of modules which are installed on the houses can deliver us energy. And we will talk not only of what is going on today, coming from the solar energy, but of the hopes for the future. Because as you will see, the problem today in the use of energy, of solar energy, is that the efficiency is very small. So what we use out of the energy which we could use, it's less than 20%. And this makes so that if we would be able, and the research focus on this in present days, if we would be able to double this factor, of course keeping the costs limited, we would achieve a double energy release out of the sun, which it's heating us, but it's not only heating us. Well, a part of that, the solar energy is the only energy we can use when we, not the only, but the most efficient and the one which makes us mostly independent when we try to travel in space. And most part of satellites present day are using huge solar panels which are giving the energy to the module which is coming from the sun. And you have heard recently, which was called the biggest achievement, scientific achievement of last year, was Rosetta and Philae, so which landed on this comet, which I don't say the name because I'm saying it very badly. So that kind of achievement was only possible due to solar energy. So solar energy was powering Rosetta to get there. Actually, it was staying in hibernation for a kind of 2 years before when it arrived after Jupiter, and it was rather thrilling when the solar panels expanded again last year in approaching the moment when Rosetta would have arrived near the comet. And moreover, then when Philae landed on the comet, as you might know probably, the problem was that it bounced 2 times and then it went in the end into a different place than the one originally proposed. And there the problem was that the solar panel, it was in shade and could not get enough solar energy to remain alive. So the only things which could have been done, and there are many, were however done with the batteries which were on board, which could have lasted almost 3 days. After 3 days, now it's sleeping with the hope, which is not too high to be honest, but still it's some remote hope that when well, in August, the comet will arrive near to the sun because it's approaching and approaching. When it will be very near, it will be enough, the energy which the batteries are receiving. However, I have to tell you that this type of batteries are very different with respect to this type of batteries with solar panels. in the sense that here, as I told you, the efficiency, it's low. It's something like 14, 15% most usually, while here the efficiency goes about 40%. Of course, in order to do this is done just not to make the solar panels far too big, 100 meters, we can't afford that, so they are much more expensive. That's why we don't have on our houses this type of materials, which I'm going to mention. So they are much more expensive, but for the space, it's a must to go in this direction. And who knows that in the future we won't discover some other ways to use not only the energy from the stars, but maybe some other physics principle to allow us, for example, not only to travel in the space, but to pump up with energy our vehicles in the space. Now I'm going to start with, even if you have heard from Fabio Sciarino on quantum mechanics, I'm going to tell you some additional things. Because on quantum mechanics, since there are so many open questions and puzzles, it's never too much to speak about. You see, the quantum mechanics, it has a very, very clear and rather simple, even if it can become very complicated, mathematics to explain things. However, related to the meaning of that things, what in the end does it mean? It's still a lot of discussion, not only in the community of physicists, but in the community of philosophers as well, and mathematicians. Here you have names of persons who have contributed the most to the development and to the birth of quantum mechanics. I underlined Einstein because one of the pillars, which is the photoelectric effect, it's the one which is related to the second part of my talk, namely the solar energy. So, differently from the relativity, which has a very clear birth date, the very moment in which Einstein published in 1905 the paper related to the explanation of the weird phenomena, which could found a natural explanation in the fact that in the end you have the constancy of the velocity of light, and that made things to come very naturally in a framework which is the relativity. The quantum mechanics has many fathers. As you see, no mother. But anyway, we are in a modern era, so there is one child which is quantum mechanics, which all these people contributed, and I'm sure that the list is not yet big enough. Here you can see a picture taken in the most, I dare saying, most famous conference in the history of physics, certainly in the history of quantum mechanics. It's the conference in Solvay in Belgium, in Bruxelles, and Solvay was an industrial person, so he had an industry, but he was a very open-minded person. There are very few left nowadays, not that there is known, but there are still very few persons who are doing they spend their money to create other money, so they do industry, but in the same time they spend some money for the science and for looking forward, because this is the way to go if you want to achieve further progress. You can't rely only on what you have to get more. And in this sense, you see here, with the names on them, those who were mostly contributing to the progress and to the development of quantum mechanics. You have heard yesterday about Dirac in the antimatter talk of my colleague, and you have heard already the name of Planck, of course. And here you can see as well some other two key persons like Bohr, Niels Bohr from Copenhagen, and Einstein. I underline them because probably part of you know, there was a debate in the history of quantum mechanics related to the meaning of the things which we are thinking about, the micro world, which generated an intensive discussion and debate which never ended. So these two guys are not with us anymore, but their ideas, their thoughts, and their proposal are still here. Another guy I'm going to briefly mention is Schrödinger, who was the father of the most easy equation in quantum mechanics. So the Schrödinger equation, which is introducing this very difficult concept of a wave function, which we are still debating of what does it mean. So I'll come back to this. So the quantum mechanics, it's a theory, very easily, very simply said, that describes the behavior of the very small objects. Which are these very small objects? Even if object, it's already, one can debate for a long time on the concept of object, because as you will see in quantum mechanics, an object, it's a wave or it's a particle, so we go deep in the heart of the quantum mechanics by even mentioning the word object. So what are these particles? They are really what we call now elementary particles, like electrons, neutrinos, and so on, the atoms, molecules, bigger and bigger molecules, but we don't know if the behavior described by the wave function is extending towards bigger, 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 only if we could do the experiments. So we are not yet sure whether quantum mechanics is a universal theory which would be valid if we could do the experiment for, let's say, for a ball when we play the soccer. What does it mean, as you will see, and I'll come back to this, what would mean to have a quantum mechanics when we play soccer? And here I will briefly mention the Schrödinger cat paradox, which brings me to this where is valid the quantum mechanics? Is there some limit of validity? You see here one of the guys who was working in this theory in the very beginning, Werner Heisenberg. I mention him because of the historical item as well involved here. So we are not doing physics out of the world, but we are doing physics inside the world. And Heisenberg has a very weird story because he participated in the Second World War. He was one of those mostly involved in the German project of building the nuclear bomb. And it's strange because apparently they have missed, fortunately, the equation by an order of magnitude. So they arrived to the conclusion that the quantity of the material which is necessary to build a bomb is 10 times bigger than in principle should in reality is. And this discouraged them very much. It remained rather, let's say, at least for some people, dubious why they did this kind of trivial mistake. Well, it's not trivial, but however, for the capacity of Heisenberg. So somebody was putting forward the hypothesis, to be honest, not so trustable, that he did it by purpose. So it's not very clear whether this was the case or not. However, so physicists are not out of the society, and they contribute not only to the progress, but sometimes, unfortunately, to bad things which happen in society. So that was definitely the case of the bomb. So the burst of the quantum mechanics, as of any theory, a part of some modern theories which are, well, still trying to explain facts in nature which cannot be explained by the theories which we have in hand, was triggered by a series of strange experimental findings. So among these, it was accumulating and accumulating facts which could not absolutely be described by the classical mechanics. Classical mechanics, the one which has the founding fathers, Galileo and Newton, and it's perfectly working when you are not dealing with small objects or when you are not dealing with objects moving very fast. So these findings are the black body radiation, the atomic spectra. Why on earth we should have only lines in the atomic spectra? One should have waited. It's if indeed the electrons are behaving like planets in a solar system, we could have necessarily waited to have a continuum spectra. Why electrons should have stayed only in definite energies? So this was a puzzle in the framework of classical mechanics. And last but not least, the photoelectric effect. So these are the facts which I'm not going to insist upon. I will only speak about the photoelectric effects, but which put a pressure, a theory change when the pressure is strong enough to make a progress. And that's the reason for which we had to invent a new theory which described this feature without unnecessary complication. And each one of these would be worthy to its own story, dedicated story, and I advise you, those who probably many of you know already, to look into black body radiation and to atomic spectra and look how these things were dealt with in the quantum mechanics. So the photoelectric effect, it's dealing with coming back of what is called the light particles, so the particles which are composing light. It's coming back because by the by that time, beginning of last century, was rather clear that the light is a wave. Everybody agreed that the light is a wave because the light is interfering, the light is doing diffraction, and many phenomena which are belonging only to the waves. But at some point, some findings, and in this case, since part of you were doing the experiment, right? You were determining the Planck constant. So you did this experiment when you were having radiation of different color, which was impinging on a piece of metal, and the electrons were popping up. Electrons were popping up. This is not weird. It would have happened when the light is radiation as well. What was strange was the features of the way of the electrons which were coming up. And well, among these, the instantaneous emission of no delay, well, this is rather weird, because one should have expected that if the wave is coming, there is some time needed to shake enough, like in a boat. If you go out of the boat, you might wait a bit till the waves are accumulating and give you the energy to shake you away. But even more mysterious was the fact that the kinetic energy of the electrons did not depend on the intensity, but only on the frequency. And this could not be explained in the framework of the image of light as seen as a wave, because a wave could have, if you would have waited long enough, the energy would become at some point above the threshold and would have shaken the electron out of the orbit of the atom. So these features were mysterious, but nobody dared to question the nature of light, apart Einstein. So Einstein was a very brilliant person, but brilliant not only in what he created, brilliant in questioning things which were given for granted by other persons. And that's a typical case of what he did. So he came back to an interpretation of light as being composed of particles, Lichtquanten, and he proposed that the light, as indeed was initial proposal of Planck, but Planck was used it as a game, as a kind of, let's say, he was not absolutely, Planck was not saying that light is composed of quanta. Planck was saying, if we imagine that we use this mathematics, he would never dared to question the nature of light, which was, however, done by Einstein. So he took for granted, and he took seriously, the hypothesis of light being composed of particles, and he explained very naturally, as you have seen, and as it's rather easy to get, he explained this feature by seeing a light composed of photons. This name was coming later on, which now everything comes clear. It's a kind of kickoff. The energy of the extraction of the electrons should be subtracted, and what remains is part of a difference between the energy of the photons and the energy necessary to extract them. Of course, that people did not immediately believe Einstein. Why should have they believed them? After all, Huygens and many others were explaining very clearly, and all our experiences were showing us that the light, it's a wave. In spite of the fact that time before Newton, but well, Newton certainly did not think about photons, his view of the light was definitely a particle-like view. So Newton explained light as being composed of particles, but this fell down immediately after Huygens was explaining light as being composed of waves. So of course that people didn't rush to believe, oh, Einstein, yeah, you're right. Now light, it's indeed, we were wrong for 200 years. Now you showed us the right way. So nobody really, well, many did not really believe until Compton came. So the Compton effect, did you study? Who studied the Compton effect? So the Compton effect was studied by a huge percentage of 2% of this room, 3. The Compton effect, it's an effect where you come with a photon, you kick on an electron, and then you get another photon, but with a smaller energy. It's a kind of an elastical scattering of a particle against particle. And this, of course, cannot be a wave phenomena. This phenomena is definitely a particle phenomena, because you have a kind of elastic scattering, bang, bang, so you see it. So when Compton discovered that you get a kick, so you don't get a, whoa, whoa, I'm shaking, and look at me. It's a kick once at a time, and you get the photon back with smaller energy, and you get another electron with another energy. Then everybody believed that. So now what's the problem? We have phenomena where the photon, it's a particle, and we have the phenomena where the photon, it's a wave. I have to tell you that we still don't know why this is happening. Of course, that if in my place would be another colleague of mine would tell you that he has a solution. Unfortunately, if you'd listen 10 colleagues, they would have different solutions. So that's the problem today in the interpretation of quantum mechanics. Why on earth we have this duality? And this is the first appearance in a theory of a dualism, of a duality of wave and particle, which stays with us. Gives us not only problems, but gives us huge, enormous opportunities. And related to this, once we established that the photon is wave or particle, we started to think whether this is belonging only to the photon. Is it only the photon which is so crazy, so diabolic that it behaves in two ways? Actually not, because this behavior belongs to whatever particle small enough that we can experience on it. So what we could do was to try to do experiments with particles, so not only with light. And by the way, related to this, Richard Feynman, which is one of the biggest scientists who lived last century and one of the most amazing ones, I'll come back to him, who was having a very, very exciting life and gave to the others a very exciting life because he was a very interesting man as well. So experiments were done, and that's why he says that the interference stays at the very heart of the mystery of quantum mechanics, where you would shoot against a wall, which has two holes in it, particles from a source of particles, like, for example, a source of single electrons. What is a source of single electrons? It's enough if you hit a metal, the metal will pump up electrons, so with magnetic fields you can extract one electron at a time, and you can direct them to this wall. What is happening here? If you have two holes in it, you can close one, you can shoot your electrons, and of course they have the opening, which is here, and you get, of course, the electrons coming out only from the opened hole, which is the similar thing happening when you get it open the other one. And, well, of course, that if we believe that the electron is a particle, what we would expect is to find this behavior when you shoot in the two open doors at a time. In fact, what happens in reality is the following. This is the experiment. So if you'd be able to register their arrival on a screen and to keep it there, so to register many of them. If you have few, you don't really understand what's happening. If you have more and more, you see that strange things are happening. Actually, these strange things are that you don't see in any way two different arrivals as you would have expected, believing that the electron is just a particle. But you see something which looks very weird. It looks weird, but it's not unknown. It's only that you would have never associated it to the electron. It's a typical interference pattern, which looks like this. So the intensities of the signal looks like this. So it's not corresponding to here and to here. Why it's weird? Well, this behavior, it's typical to the waves. So if you'd have waves of water, and you can do by yourself your experiment at home, just put water in a tub and just with the finger you can create waves and you can do, this is one of the simplest experiments to be done. So you can observe it by yourself, the composition of the waves. The only weird thing was the fact that nobody was expecting it to belong to the electron. So in this case, the electron does not behave like a kind of a dot which goes there, and we know precisely where it is. We don't know where it is, in the sense that a phenomena which is a wave describes the electron as well. And this experiment has been done repeatedly, and it continues to be done. So this is what I told you, it's water, what you would see if you do it. And this is typically in nature. It happens in the big waves, in the lakes or in the sea. In the sea, of course, it's very complicated because the waves are many. It's not only an interference of two waves, it's a many, many wave interference phenomena. And this is the way in which we connect the two behavior, the particle, which belongs to momenta, mass, velocity, and something like that, and the wave behavior. When Louis de Broglie, When Louis de Broglie proposed this formula in his PhD thesis, actually people were laughing on him, and he was asking help for Einstein, and only that way he succeeded to pass his PhD, because this hypothesis that not only the photon is crazy, but the other particles are equally crazy, and it's natural, that's what he said, was considered still to be rather weird. You see, we are still in the middle of the burst of the quantum mechanics. As I told you, these behaviors are not only a problem for physicists and philosophers, thinking why this is happening, and this is ongoing. There are interpretations of quantum mechanics, there are discussions, there are experiments questioning this behavior. But it's huge, huge opportunity given to society. And these opportunities are related to future quantum technologies. You have seen from Fabio Sciarrino part of these technologies. You see here the quantum computers or whatsoever else, teleportation and technologies which are still to be born and which are worthy to be studied. We have another representative of the same type of puzzles, which is the Schrödinger cat. I don't have time now to speak about, but I only want to mention it because if some of you it's interested and curious, it's a very, very nice way to enter deep in the mysteries of quantum mechanics and see what is happening with this poor cat, which is half dead and half alive in the same time. And this is a manifestation which initially Schrödinger put forward to mock the other scientists, to tell them, look guys, you are so crazy, it can't be. But in spite of the fact that Schrödinger was proposing it like a kind of a joke which would have ended there, you see, we are still speaking about the Schrödinger cat. So I really advise you to have a look if you didn't have it already. I come back now to the part of using this radiation for our technologies. So the solar radiation, which is composed of photons, or if you want, of waves of light, can be used in our technologies and to give us energy, since part of the spectral of the component of the sun radiation, the one which we see, of course, it gives us, it can be transformed in electric power, and then we can use this electric power to pump our houses and whatsoever else. So this is the spectrum, the part of the spectrum we are using. It's the visible one, which has the wavelengths composed here. Of course, it goes far beyond, and we have opportunities to study in both ways. You will hear after my talk a project to build a laser, an accelerator, and the strongest laser, one of the strongest in the world in Romania, in this area here. But now we are still going in the visible part, and let me tell you what is going on here. So which is the energy which comes from the sun? If you look at it, it's enormous. So out of the atmosphere, so if we would be to measure it out of just on the top of the atmosphere, the quantity of energy, the power which is delivered by the sun reaching us, it's something like this, 1.3 kilowatt per square meter. You can imagine that if we'd be able only to use, of course not all, if we use it all we burn up, but even a minusculous part, a minimum part of it, this would solve the energy problem forever. Of course this is not easy, and I'll show you why. This fluctuates, but this is less important. You just have to remember that it's about a bit more than 1 kilowatt per square meter. This is a map in August, of course, of the solar energy, and you see here that there are areas which are having huge quantities. That's why maybe some of you have heard of this idea to build a huge farm of solar energy in the desert in Africa. Of course, that the region, it's technically very compelling, technically very difficult, but there are political problems. I mean, of course, if you want to do there, you should do it peacefully. Now you know which is the situation. So it's a very difficult situation politically, not only scientifically and technically challenging. The other regions are remaining with more or less sun. You see here again, there are very, this is strange enough. In Europe, the country which is mostly and most efficiently using this energy, which is not Italy, is Germany. Does have not so much sun, but they have a very clear politics to use that one. You need to combine the politic of using this energy with the capacity to do it. Okay. So how to use this energy? Of course, since I showed you and you know already, it's the photoelectric effect. It's one of the things to be used. So you transform the photons directly in electrons, but you have then not only to transform them, you have to collect them. Otherwise, you get lost. And you see here already, I show you the capacity of the materials which we are using to use this energy. So this is the efficiency, a kind of a response of various materials which we are using according to the solar spectra and beyond. So you see that, for example, the amorphous silicon goes down, has an efficiency already in green, not to speak about red, which is very small. It answers very well to the blue light, but then its efficiency goes down. That's why part of the thing for which using the actual solar panel are making us not too much energy. There are other materials like the gallium arsenide, cadmium telluride, or various combinations of these which are expanding their huge, enormous efficiency on a much broader range, and moreover, they are constant efficiency in our range. This is to anticipate what we can do in the future to increase and to do better than we do today. What we do today basically is to use the energy coming from the sun, the photons, to trigger a diode junction. So diode junction having an emitter and a base, you know all this. So you have to do this one. This is a first step in order to build a solar cell. Then you have to put some metallic contacts in order to be able to take away the signal which is delivered by the passage of a photon, and then what you can do is to take the signal out and to use it and to make it with an inverter, to insert it in the house or in the circuit of electricity you have in your house. So in the end, the photon coming from the sun goes inside the material. Usually it's used the silicon. Why it's used the silicon? Because it's the best material? No, it's not the best material. It's the one we know better. It's the one we know better because all our technologies are developed on silicon. But there are people who start to work in other material research in order to be able maybe to find some of them which are responding better to this. So it's delivered an electron and a hole. This is the typical process which is happening in a semiconductor material. And if you collect them, if you have the potentials and you drove them, each one to its own electrode, you can, in the end, succeed to get out power, which is transforming directly the light from the sun in electric current. So here you see how it's more or less done. When you have more of them, you have contacts, front contacts, the junction itself, and the back contact. You have some anti-reflex, so it's a lot of research which is trying to improve the way in which the signal is delivered. In the end, what you want to do is to do, well, this is how usually they look like. So 36 cells all together, you collect the signal all together in order to arrive something like 12 volt per module, and you then encapsulate them in order not to make them sensible to the weather or to other conditions, put them together, and you have many modules put either in series or in parallel, depending what you want to do. And this is how it looks like. So this is rather standardized technology. In order to be able to replace one with the other, you have these modules I showed you about, and you install them more together in order to be able to have a bigger signal. This is the history of what have happened in these years with this is not red, but I'll tell you. So this is what happened in the lab. So in the laboratory, the efficiency of using silicon evolved like this. So when I do in laboratory, in yellow, it's what is happening in the real life. So when you do the things and transport them from the laboratory, where you are very careful, you pay attention, you do things at best you can, but you put it on the house, you get an efficiency which drops from 20–25%, which you might reach in the laboratory, to around 15%. So this is where we are today. So that's why those who are having a house where they put these panels need to have many square meters in order to get something compelling. Because what does it mean? So we had 1,300 watt on the top of the house, on the top of the atmosphere. What filters, it's something like, let's say, a half. So let's say we end up with 700. 700, then you have 15% out of it. So you have 100 watt, a bit more than 100 watt or something per square meter. So if you want to have a kilowatt, you need to put 10 meter or so on the top of the house in order to have something reliable. Which means that if we would be able to increase this efficiency, this would be really a turning point in this kind of technology. Which brings me to the, so now this is the first generation based on silicon, because that's what we know. This is the simple and very true, honest answer. We know it, we use it, but we could do better. We could do better, and now people are moving towards studying more and more the second generation, and even thinking about the possible third generation, which, however, needs new concepts. And I'll show you some driving lines for what concerns the second generation, which we could go. So the present technology, it's using silicon, and it goes from the crystalline silicon to amorphous silicon, which the technology is mature. That's the basic main advantage. So we have a mature technology, we know how to use it, we can use it. The drawback is that the efficiency, it's small. Now, efficiency here was quoted like 10%, now it goes a bit better, but it's still small. Then we have these other materials, which is a combination of materials, cadmium telluride or with sulfur inside, with indium, with gallium. It's called thin films because really they are very, very differently from silicon, which is rather thick. These thin films are thin layers, are sandwiches of layers which are micron thick. So they are really very thin. And this has higher efficiency. Maybe one can reach small costs, maybe. But the technology, at least today, it's not yet mature. So in order to create these thin layers, you have already few proposals. We are having here in Frascati, for example, a group which works in this, trying to get a better technology to create these thin layers, because you have to grow them up somehow. So you have to grow them up somehow in order to do a sandwich where you put all these things you see here together, and you see it's angstroms or microns. They are very thin. The research is worthwhile, not only because we might get panels which we put on the house and we get twice the energy, but can you imagine if we succeed to manipulate this technology and to get it thin enough? Moreover, you might get it transparent. This is one of the other things. You can get it transparent materials. You can put them on the window. So you have in architectural, nice ways, not only to put them there and to make your buildings nicer, but to get energy out of them. So you can put them on the window, you open the window, it's rather transparent, or you can even get it a color, you can put some color inside, some pigments, and you get a very, very nice looking like object, which in the same time gives you twice, this is the hope, twice more energy than you can get today. The research, however, is very difficult. It's difficult because you have first to find the best materials, and just find the best materials, it's in itself a compelling problem. And then the problem is, once you have this combination of materials, you have to get it on the substrate and to collect the energy coming from it. And this is, again, a very problem which, as Melina was saying, puts together many, many challenging people from many groups, which are coming from chemistry, material science, engineering, physicists, mathematicians, and so on and so forth. And so what limits our efficiency? There are many factors. Part of it goes in heat, of course. So you never get ideal process perfect. So you get loose part in heat. the diode and the materials are not perfect, so you have defects in the materials, and this eats you up, even badly destroys your cell. So if you would be able to solve these problems, and this is a kind of a hope concept more than a hope reality, a hope concept for the third generation, you can reach a theoretical efficiency which is very high. It's something like 6 times higher than the today technology. This is how it looks like, at least the panels we have today. The thin layers is not yet really a widespread technology, but this is what we have. We can put them in the airports, we can use them in different ways, and we can put them, of course, on the houses, and this is the use which is mostly done with the inverter. You get the energy back into the circuit and to the electrical contact. First you have to do a certain modularity, then you install them, and then you get the power. So that's how it looks like, and you have seen probably many. You might have not seen them in vertical. This is a 3 kilowatt power in Portici in Enea. This is in Rome in a house, a possible way not put on the roof, but a farm near the house. This is again on the house, in the airport again, or we can use them. This again, houses in Australia, for example. Now I jump this. Now, this is definitely not only an opportunity for the rich, still rich Europe. It's an opportunity for poor countries. Poor countries like what? Like Congo Republic. In these places where you have nothing else to do, you don't have waters, you don't have nuclear power plants, this is dangerous to have them there. So you have nothing to produce energy, but you have something of which they are extremely rich, the sun. So you can put them there, even silicon, it doesn't matter the area in the desert, it's big, so you can put them these devices. This is in Egypt, so you can get on the petrol platform, so you can get a huge resource, so it can contribute to develop and to grow the world, which is not yet at our level, and it's far from being at our level. So gives an opportunity to poor people to get electricity, and electricity really changed the life of persons. So this is one thing which is definitely an opportunity. Then you can integrate it and use small quantities in very nice way. Actually, I've been in Hamburg last summer, and I've seen something I remained there, wondered for. It was a garbage box which was opening, was functioning with the solar energy. It was very, very nice and very funny. So this is a kind of a map of the installed power. You see it's growing, but it's still, let's say, I don't want to enter in detail. This is the watt per person. It's already old. Today's situation might be a bit changed. This is a medium amount of watt per person produced in different regions of the world. We see that there are huge regions where sun is there, but there is nothing, and so on and so forth. So this is what has been produced by thinking about how the world goes. Einstein was one of those, and definitely was the one who explained the photoelectric effect, and his weird explanation, the photon as a particle, stays at the basis of our technology, and definitely was making him more worthy of the Nobel Prize he got for this discovery. This is him together with Niels Bohr in the perpetuous discussion they had, and which we are continuing, of what's the meaning, the deep meaning of these discoveries, which goes far beyond the technology which we are using. It goes back even to this phrase he said, God doesn't play dice, and that was referred to the probabilities, which is another item, which, however, brings me to the interpretations, and for who is interested, I can recommend some books related to the meaning of this, among which there is, they are very different among them. It includes these parallel universes, many world interpretation where things are explained by a splitting of our universe in many universes each time you try to measure something. So I want you to take back home the message that quantum mechanics, it's not only here with us now, and it's with us in our computers, in our CPU, in our wherever, and solar energy, but it stays and will definitely stay at the basis, at the many future technology, some of them we might not even imagine today. And for those who have seen this movie, it was already supposed. So this guy was moving his brain, he was dying, and his brain was moved into a quantum computer. Quantum computer because it needs too much power. So the quantum computer hosted his brain and developed by itself, questioning what the artificial intelligence might bring us. It's in competition or not with our intelligence. So this is a nice movie where the quantum computer was given for granted. So if we now believe this is a consequence not only to my talk but to my previous colleagues' talks as well, that we have a kind of an image of the universe, and we believe that the image of the universe is kind of a banana, and we believe that for the moment we have half of it and we wait to discover the other half of it, what we might discover is that the universe is not a banana, but it's something else. Who has to do this? Well, since many of you want to study physics, it's up to you. You might discover something new. You might question things we give for granted. And actually, I hope that you will do so. And this is what that's why we need you. The society needs you, not only we. And I end with this nice poetry of Feynman, which was the guy who was saying that the mystery of quantum mechanics is the interference, and he was writing this nice poetry, and I only want to read the last part. Out of the cradle onto dry land, here it is standing. Atoms with consciousness, matter with curiosity. Stands at the sea wondering. I, a universe of atom, an atom in the universe. And that's what we are, and that's what we are trying to do, trying to get some amusement as well. Thank you very much.